All right, so we're starting chapter 3 now. I will talk about section 2.6. I skipped it for now. I'm going to do that section. I might make it an extra credit type of section for the homework and attach it to the next homework assignment. But for now, I'm going to go ahead and skip it and jump to chapter 3 so we're on schedule. So section 3.1 deals with extrema on an interval. In this video, I'll just discuss the concepts. Following videos will be going through examples. All right, so for the concepts of this section, one of the things is dealing with local min and local max, which sometimes it's called a relative min and a relative max. And so in this first picture I drew, this is the curve is the function, and right here at this dot where it's in yellow, this is a low point to the graph. So that's basically a local min. And the local min is the point C comma f of c. So c is the x coordinate, f of c is the y coordinate. Similar to this one, this has a graph depicting a local max or relative max. And this is just the highest point to the graph is right here. And I'm only looking at a narrow scope of the graph also, that should probably be said. So I'm considering it relative or local in the sense that I'm only looking at a narrow scope of the graph. But these are two pictures representing the local min and local max. Now extrema on a closed interval AB, you're going to have something called an absolute min and an absolute max, or sometimes called global min or global max. Now there could be multiple relative mins and there could be multiple relative maxes to the graph if you're looking at not into a narrow scope, but just in a wider interval. And the absolute min or global min is either going to be the lowest relative min on the graph or the window that you're displayed on, or it can be an endpoint. Similar, the absolute max is either going to be the highest relative max or it can be an endpoint. Again, we're looking at a more wider range of values, whereas these are just sort of local or just very narrow window. So I drew two pictures. And the first picture, so notice my closed interval go from A to B. Those have brackets, and then the endpoints, f of A and f of B are closed dots. So these are endpoints. Whereas the pictures from before, I had arrows to indicate it goes on forever. Now, the graph itself could go on forever, but we're specifically focusing on the interval from A to B as far as what the graph does. And what I have here is a relative max. It's a high point. It's a local max around the values that are close to it. This is a relative min. It's a low point. It's lower than some values that are around it. And then this is a relative min. And because it's a high point, higher than the values that are close to it. Now notice I have two relative maxes. This one, C3, f of C3 is the y coordinate of that. That is the largest relative max of the two. So that's why it's called an absolute max. This one, there's only one relative min, but it happens to also be an absolute min. All right, it's the lowest of the relative mins. Well, we only have one relative min, so it's a relative min and an absolute min. Now this picture I drew, you have a relative max, relative min, relative max, and a relative min. Now, as far as the max values go, between C1 and C3, C3 has the largest relative max, so it's a absolute max is this point. For the mins, I have C2 and C4. These are relative mins, but notice I have the endpoint being lower than the relative mins. So in this case, these are just relative mins, and the endpoint itself is a absolute min. We will never say an endpoint, so that is a comment. An endpoint can never be called a relative min or a relative max. It's only absolute. All right, that's if it's applicable. And in this picture, this endpoint is lower than the two relative mins. It's the lowest point to the graph itself in this whole window. And so that endpoint, f of a, is the y-coordinate of the absolute min. All right, so it's just drew this just to show that the absolute min, or you could have the absolute max, but not in this case, could be an endpoint. But the endpoints themselves are never called relative min or relative max. All right, so that's some of the concepts for extrema. Extrema just means extreme values, and that's either a minimum or a maximum. Now the next thing in vocabulary is critical numbers. Let f be defined at c if the first derivative at c is equal to 0, or if f is not differentiable at c, so that means the derivative does not exist at c, then c is a critical number. All right, so I drew two pictures. The first one, this has f prime of c, and then d and e does not exist. So you have this cusp-like thing going on to the graph, and there's no way you can draw a horizontal tangent line to this point. Any tangent lines you draw, is closer and closer, are just going to get sort of, they don't converge to a single tangent line. So can't draw a tangent line at this point C, where the y coordinates f of c. So the f prime of c does not exist. Whereas here, this is an example where you do have a tangent line, horizontal tangent line, and that's this dashed red line. So at C, it's got y coordinate f of c, the red dashed line is a horizontal tangent line. And we know the derivative gives the slope of a tangent line. So if you have a horizontal line, the slope of a horizontal line is 0. So that's why it says f prime of c is equal to 0. So that's that kind of case. And notice just based on our rough picture, this would be like a relative max. And then this is a case, again, where the derivative doesn't exist at c, but yet it's still a relative max, and that's a critical number. Which leads me to the next theorem. Theorem 3.2 just says relative extrema occur only at critical numbers. All right, that's just what I sort of drew right here. These are relative maxes. So if f has a relative min or max at x equals c, then c is a critical number. That's what the theorem says. So that is all the terminology. Now, what we're going to do in this section is essentially find critical numbers and then determine from the critical numbers what the absolute min and absolute max are to the graph on some closed interval. All right, so this is the guidelines for finding extrema on a closed interval AB. The first step we do is find all critical numbers on the open interval AB. So we only look at the values in between A and B for the critical numbers. The second thing is you evaluate f at each critical number in AB. So that just means to find the y coordinate corresponding to each critical number. So when it says evaluate f at each critical number, you're just finding the corresponding y coordinate for the critical numbers. This third step is to evaluate f at each endpoint. And again, for the evaluate part, you're just finding the y coordinate of the endpoints. And then the thing is, all right, so you found these different y coordinates. And so the lowest or the least of these is going to be the absolute min. The greatest of these is going to be the absolute max. That's the guidelines. And so I'll show an example going through the guidelines. And in the next video, I go through several examples, or next couple of videos, several examples where you'd find examples where you find critical numbers, determining relative min, relative max, and then this determining absolute min, absolute max. But this captures all of it when it's finding absolute extrema. So I'm going to find the extrema for the function f of x equals 3x to the fourth minus 4x cubed on the closed interval -1 to 2. So our guideline says the first thing we do is find all the critical numbers on the open interval -1 to 2. All right, now what it meant for it to be a critical number. Well, critical number, it's either f prime of c is equal to 0 or the derivative does not exist at c. So c is a critical number if its first derivative is 0, or the function first derivative is 0 at c, or if the derivative does not exist at c. So that's what a critical number means. So if I need to find these critical numbers, I need to find where the first derivative equals 0 or where the first derivative doesn't exist. All right, so in order to do that for those particular values, I have to first find the derivative itself. And that's what's going on here. So f prime of x equals 3, and then I use the power rule. Drop down the 4, so it'll be 4 times x to the 4 minus 1 from power rule, which gives you 12x cubed. And then for the other term, where it's minus 4x cubed, you drop down the 3, so it'll be minus 4 times 3x to the 3 minus 1, which is negative 12x squared. So this is the derivative. All right, now it's a polynomial. It's not going to have any cases where the derivative doesn't exist. So we only need to focus on when the derivative is 0. All right, so then we set our derivative function equal to 0 and solve for x, and that will give us the critical numbers. So that's what I did here. I set 12x cubed minus 12x squared equal to 0 and solved for x by factoring. So I factored out 12x squared, and then I got times x minus 1 equal to 0. So I have two factors. The 12x squared set that equal to 0, and then the second factor I set x minus 1 equal to 0. So the first factor, when it's 12x squared equal to 0, you get x being 0, and the second factor with x minus 1 being 0, you get x equals 1. So these are my two critical numbers. All right, so that is the first part of the guidelines. I find the critical numbers, and that involved finding the derivative and then finding the x values where the derivative is equal to 0. The second guideline is to evaluate f at each critical number, which means to find the y coordinate of the critical numbers. So we have 0 and 1. You plug 0 and 1 into the original function and see what y coordinates you get. So when you plug in 0, you get 0 for its y coordinate, which means you have the point 0, 0. For the other critical number 1, when you plug in 1, it simplifies to give you -1. So that's the y coordinate's -1, so the point is 1, -1. All right, that's the second part of the guidelines. The third guideline is now to evaluate the function at each endpoint of the closed interval. So basically find the y coordinates corresponding to -1 and 2. So I plug those two values into the function. You get a y coordinate of 7 when you plug in -1. You get a y coordinate of 16 when you plug in x equals 2. So now I need to determine what the absolute max and min are. So I went ahead and listed all 4 points. 0, 0, 1, -0, these came from the critical numbers. -1, 7, and 2, 16, these came from the endpoints. So -1's the lowest y coordinate of all the points. So this point, 1, -1, is the absolute min. 16 is the highest y coordinate of all 4 points. And so the point 2, 16 is the absolute max. And that's how you determine the absolute extrema on a closed interval. And this example pretty much captures all of the concepts. So the next video we'll be going through examples. This is just first demonstrating the concepts.